Hello everybody. In this video, we will explain how to determine the electrical field caused by a continuous distribution of charge. In this problem, assume that we have this arbitrary volume which exists in the free space, and this volume is charged, and we wish to determine the electrical field caused by this volume at point P. Simultaneously, you are going to tell me to calculate it using this equation right here, and apply this like this over there for each point inside this volume, and then add all of these contributions together to find the electrical field. Okay, this is going to work only for discrete separate charges like over there, but in our case, in this volume, we have a continuous distribution of charge, which will end up with adding an infinite distributions of electrical fields due to this infinite distributions of charge over there. So we must pursue another approach to find this. Okay, in this case, we will take a differential value. We are going to take a differential value from this big arbitrary volume. We will call this small differential value by d v primed, as this whole volume is v primed. Okay, v primed is the whole volume for this arbitrary volume for this arbitrary shape, a three-dimensional shape, and dv primed is the small differential value which has an infinitely small volume tends to zero. Okay, now we want to calculate the electrical field. Let's choose the red color. Okay, now we want to calculate the electrical field caused by this small differential value at point P. Okay, the distance between them, let's call it by r, and of course, as it's r, so it's radial. It's as the direction of the electrical field is along the distance between them. Okay, now just apply this formula. The electrical field is equal to the charge. The charge of this small differential volume is equal to this volume. Okay, the charge of this small differential volume is equal to this small differential volume times the charge per unit volume for this small area, which is the charge density. Okay, where rho sub v is the charge density. Okay, the charge density or the charge per unit volume times the volume is going to give us the charge, which is Q, the charge inside this small area. Okay, divided by 4 pi epsilon divided by the square distance between this volume and P, which is r squared. Okay, and the direction of the electrical field is a sub r. As this equation is the electrical field for small differential area, so the electrical field is going to be also differential for small negligible area. Okay, now to find the total electrical field in this big volume v primed, we want to take the integration for both sides. Okay, now when we integrate this part with respect to E, is going to give us E. Okay, this is vector, and so this is vector also. Okay, equals, now this 1 over 4 pi epsilon sub 0, all of these are constant, so we can take them out of this integration, but otherwise are not constant. For example, this charge density is not constant because the charge density is not distributed, is not necessarily distributed uniformly over this volume, and also R is not constant, because if we took another, for example, this small differential value, the distance is going to be different, and also the unit vector is going to be also different. So these are not constant, the otherwise are not constant, otherwise are functions of volume. Now we can use this equation for we can find this equation to find the electrical field caused by this volume. And sometimes it's so hard to find the unit vector a sub r, so we want to use another type of equation. Okay, as we know that the unit vector a sub r is equal to r, this vector, divided by the modulus of this vector, which is r. Okay, now we can substitute the right hand side for this equation in this equation, and we will end up with as we saw before. In order to find the electrical field due to a 3D distribution of electrical charges, we are going to use this equation. We are going to integrate with respect to the volume. We are going to integrate with respect to xyz in case of Cartesian coordinate system, or r theta rho in case of spherical coordinate system, and so on. And let's consider another case of problem. We have a charge distribution over a surface. Our process to find the electrical field is going to be homogeneous to what we did for the arbitrary volume. We are going to take a small differential piece of area from this surface, which is ds primed, and we will consider in this case the charge per unit area, or the charge density over this small surface. And then we are going to integrate with respect to surface. We are going to integrate with respect to 2 dimensions. And in case of charge distribution over an arbitrary path or line, the same thing will be. We are going to take a small piece from this path, dl primed, and we will consider the charge density for this path, or the charge per unit path, and apply this formula. We are going to integrate with respect to the path, with respect to 1 dimension. And this is what we have for today. See you later.